We just got done learning about the ideal gas law, PV equals nRT. And most of the gases, however, we encounter in the world, whether it be with chemical processes or just breathing air, it's never a pure gas. That's a very rare occurrence where you're dealing with a pure gas. So how do you handle gas problems and make decent gas predictions regarding pressure and temperature when you have different types of gas, all in the same mixture? Well, that's what we're going to talk about today with partial pressures. And a good example of this is when you go diving, right? At 1 atmosphere pressure, here's the partial pressures of oxygen and nitrogen in your lungs. And when you go just 99 feet down, which is about 4 atmospheres, these partial pressures of nitrogen and oxygen change big time. So how do you do these calculations? What do they mean? That's what we're going to mess with today. Here's a static image of gas molecules striking a piston and keeping it pushed up. And this is perhaps a better animation of that same picture. You can see the moving gas molecules that keep striking the piston and keeping it up. So gas pressure is created by gas molecules striking the surface of the container, right? And the harder they strike and the more often they strike, the higher the pressure. And how do you make them strike harder and more often? Just increase the temperature. Partial pressure and total pressure of a gas. Now what's interesting about partial pressures is that if you add them all up, you get the total pressure. Let's see how this works. We have 2 containers here, and in this container we have 0.6 moles of hydrogen, and as a 5-liter volume there's 20 degrees Celsius. So if you use PV equals nRT, we can calculate the pressure, and it's 2.9 atmospheres. In the helium container, we have 1.5 moles of helium, 5-liter container, 20 degrees Celsius, so we can calculate the pressure, and it's 7.2 atmospheres. Okay, what if we combine these two? We put all that helium gas into the hydrogen container. So then, what would be the new total pressure? It's just going to be the sum. The total pressure now is just 2.9 plus 7.2. 10.1 atmospheres. So there's 7 weights. Here there were 5 weights. There's 2 weights here. The partial pressure of helium in this container is 7.2 atmospheres. The partial pressure of hydrogen in that container is 2.9 atmospheres. The total pressure, just add them up, and you get 10.1 atmospheres. That'd be my total pressure. The partial pressure of helium, which is 7.2 atmospheres, is the pressure due solely to the helium atoms creating pressure, striking the sides of the container. The partial pressure of the hydrogen is 2.9 atmospheres, and that's the pressure that's created solely by the hydrogen molecules striking the surface of the container. Okay? So the total pressure of the gas, that's the total pressure of the gas is the sum of the partial pressures of all the gases present. Right, that's what this equation is saying. The total number of moles is the sum of the individual moles of each gas. The mole fraction, do you remember X? Mole fraction of gas A is the number of moles of A all over the total number of moles of gas. And add up all the mole fractions of each gas present, you always get 1. So there's 4 equations. Here's a few more. Let's see if we can be comfortable with the ideal gas law and just putting subscripts on it. Okay? For example, total pressure, just put total on all the subscripts. It doesn't make sense to put a subscript on some of these things. For example, V. All the gases are in the same container, so they all have the same volume. So if you want the total pressure total number of moles, gas constant is the same for every gas. The temperature is the same for every gas present in a container. So those are the expressions we can write. The partial pressure of a gas is the volume times the number of moles of gas A, RT. Right? Partial pressure of gas B times the volume would equal the number of moles of gas B, RT. Okay? When we collect a gas over water, that's a partial pressure problem. Let me show you what I mean. This is a gas collection apparatus, and what happens is that there's a reaction going on in here. And these reactions always produce some kind of gas. Okay? And where does this gas go? Well, it just bubbles up through some tube and ends up here, being collected over water. So they collect the gas over water. So this is water. Okay? Now the reaction that we're going to be talking about in this problem is this reaction. Potassium chloride is heated and it produces oxygen gas. So 35 mils of gas is collected. So this is 35 mils of gas. 35 mils of gas is being collected. And they tell us the temperature and the pressure. How many grams of potassium chlorate reacted? Now there's a complication when collecting any gas over water. Since water vapor is collected along with the collected gas, in this case oxygen, the measured what is always too high? The measured pressure. Because we want the pressure due to just oxygen. We don't want the pressure due to oxygen and hydrogen. So to solve these problems, there's several calculations involved. So here's one calculation. PV equals nRT. So if we knew the pressure due to the oxygen, we could find the number of moles due to the oxygen. Then with the number of moles of the oxygen gas, we can use the mole bridge from our reaction and get the grams of potassium chloride. Okay, so what we need is that pressure due to just oxygen gas. Well, we know what the total pressure is. That's going to be the pressure due to the water and the pressure due to the oxygen gas. Now, this pressure due to the water, we need to subtract it out. We're going to get it from a table. Okay? So that's really what we're going to do first. We're going to find the pressure due to the oxygen and then use the ideal gas law to find the number of moles of oxygen and convert that into grams of whatever we're interested in. So let's try it. My total pressure is 756. So 756 millimeters of mercury, right, has to equal the pressure due to the water, and they said the temperature was 30 degrees Celsius. That's going to be 31.8 millimeters of mercury. Plus the pressure due to my oxygen. So the pressure due to the oxygen gas is just going to be 756 minus 31.8, which is 724.2 millimeters of mercury. So that was step one. Let's do step two. So now let's do step two. Let's use the ideal gas law to get the number of moles of that oxygen. So the subscript only goes on the end, remember? That pressure due to the oxygen was 724.2 millimeters of mercury. And I need to get that into atmospheres. So I have 760 millimeters of mercury in an atmosphere. That's about 0.953 atmospheres. So 0.953 atmospheres times the volume of the container. The volume of the container was 35 mils. So 0.035 liters equals my N, which I'm trying to find. R is 0.0821 liter atmospheres over moles Kelvin. And T was 30 degrees Celsius, I believe. 30 degrees Celsius at 273.303 Kelvin. So my number of moles of oxygen is going to be 0.953 times 0.035 divided by 0.0821 divided by 303, about 1.34 times 10 to the negative 3 moles. So if I have 1.34 times 10 to the negative 3 moles of oxygen, I can use the mole bridge to convert from moles of oxygen to moles of potassium chlorate, and then use molecular weight to get it into grams. 1.34 times 10 to the negative 3 moles of oxygen. How many moles of oxygen do I have for every mole of potassium chlorate? Get that from the mole bridge, from the reaction, and then the molar mass of potassium chlorate. I'll get it into grams of potassium chlorate. Okay, so in my mole bridge, I have 2 moles of potassium chlorate for every 3 moles of oxygen. And the molar mass of potassium chlorate, potassium is 39.1 plus chlorine 35.45 plus 3 times 16, about 122.55. So in the end, you get about 0.11 gram potassium chlorate. So collecting 35 mils of gas in this apparatus, we knew the pressure and we knew the temperature. We subtracted, this pressure was too high because it also collected water. So we had to subtract out the pressure due to the water. So they always have to give you a table of all these water pressures so you can do that. The vapor pressure of water at different temperatures, they need to give that to you so you can subtract out the pressure due to water. And once you subtract out the pressure due to water, you know the pressure due to that gas that you're interested in. Substitute it into the ideal gas law, solve for moles, and then use mole bridge to get what you're interested in. Calculate the total pressure in atmospheres of a mixture of 0.02 moles of helium, 0.01 moles of hydrogen, and a 5-liter flask at 10 degrees Celsius. PV equals nRT. We're interested in total pressure, so I put subscripts, my total pressure times the volume, 5 liters, has to equal the total number of moles, 0.02 plus 0.01, R, 0.0821, and T, 283 Kelvin. About 0.139 atmospheres would be the total pressure. What volume of carbon dioxide gas at 21 degrees Celsius and 781 millimeters of mercury could be absorbed by 327 grams of copper hydroxide? They're after volume. So you know we're going to use PV equals nRT. But we need to plug in the number of moles of carbon dioxide and the pressure of carbon dioxide. Since carbon dioxide is the only gas, this pressure, that is the pressure that's solely due to carbon dioxide. So we know that. Volume we're going to try to find. The number of moles of carbon dioxide. Let's just use the mole bridge. Because we know we have 327 grams of copper hydroxide. So we can convert to moles of carbon dioxide. We know the gas constant, we know the temperature, we're good to go. So let's start out by converting those 327 grams of copper to hydroxide into moles of carbon dioxide. 327 grams copper hydroxide. So first we'll convert it into moles of copper 2 hydroxide. And then we'll use our mole bridge to get it into moles of carbon dioxide. And we stop there because that's what we want N to be in. Copper 2 hydroxide, 63.545 plus 32 plus 2.02, about 97.57 grams in a mole of that stuff. And in carbon dioxide, we've got 2 moles of carbon dioxide for every 1 mole of copper 2 hydroxide from the reaction. 6.7 moles of carbon dioxide. Now I'm ready to substitute it into the ideal gas law equation. Pressure is in the wrong units though. 781 millimeters of mercury in the wrong units. I need to get that into atmospheres. About 1.03 atmospheres. Okay, now I'm ready. PV equals nRT. My pressure is going to be 1.03 atmospheres. The volume is what I'm trying to find. You found the number of moles to be 6.7 moles. The gas constant is 0.0821 liter atmosphere over mole Kelvin. And the temperature is 21, which is about 294 Kelvin. So I'll take 294 times 0.0821 times 6.7 divided by 1.03, about 157 liters. Here's another collecting gas over water problem. See if you can solve this. If 3.85 liters of carbon monoxide was collected over water at 25 degrees Celsius and 689 millimeters of mercury, how many grams of this compound were consumed? Okay, so remember, we're going to get the moles of this. Get the moles of the gas. Right? Using PV equals nRT. Right? Just make sure you use the correct pressure, right? Because we know that the pressure is too high because water was also collected. Once you get the number of moles of the gas, use the mole bridge and molar mass to get your final answer. Grams of that compound. Try it. See if you can get the right answer. Okay, I'm going to use the ideal gas law. PV equals nRT. And I want to use just the partial pressure of carbon monoxide. That has to be the number of moles of carbon monoxide. But I need to get the right pressure. So let's get that first. My total pressure has to be the pressure of that carbon monoxide plus the pressure of the water. My total pressure was 689 millimeters of mercury. I need to get that pressure of carbon monoxide so I can plug it into the ideal gas law. That pressure due to the water, the temperature was 25, so here's 25, 23.8 is the pressure due to the water. So my pressure due to carbon monoxide would be 689 minus 23.8. You get about 665.2 millimeters of mercury. So let's convert that into atmospheres. Divide by 760, about 0.875. So I'm ready to plug into my ideal gas law. My pressure is 0.875 atmospheres. The volume that was collected of the gas was 3.85 liters. And that's equal to the number of moles of carbon monoxide. The gas constant and temperature was 25 degrees, 298 Kelvin. So what's my number of moles of my carbon monoxide? 0.875 times 3.85 divided by 0.0821 divided by 298, about 0.138 moles. Okay, so now I can use my mole bridge to get my final answer. 0.138 moles of carbon monoxide to the moles of what I'm interested in. Now, what am I interested in? I'm interested in grams of this compound, HCHO2. So to get it into grams, I need molar mass. Okay, so my mole bridge is 1 to 1. My molar mass of this compound is 2.02 plus 12.01 plus 16 times 2, about 46 grams in a mole. So you get about 6.35 grams in the end of that compound. What volume of ammonia at 15 degrees Celsius and 1.15 atmospheres is required to produce 150 grams of ammonium sulfate? And here's our reaction. So they want to know volume. So we're going to have to use the ideal gas law. Now it looks like the only gas present is ammonia. So if I put ammonia, I need to have those subscripts are always on P and N. I'm going to solve for volume. Do I know the pressure due to the ammonia? It's not being collected over water or anything like that, so it's just going to be 1.15 atmospheres. The volume, that's what I'm trying to find. The number of moles of ammonia, I'm just going to use the mole bridge, molar mass, that's right here. And I'll convert. Gas constant, I know. Temperature, I know. Not a problem. So try it. See if you can get the right answer. So I have 150 grams of ammonium sulfate. And I want to convert that all the way to moles of ammonia so I can plug into my ideal gas law here. So I got to get it into moles first so I can use my mole bridge. So that means molar mass of ammonium sulfate. Okay, then I can use my mole bridge and then that's where I want to stop. I don't want to go to grams of ammonia. Molar mass of ammonium sulfate. I need 2 nitrogens, 14.01 times 2 plus, and I need 8 hydrogens, 8.08 plus sulfur and 4 oxygens. Sulfur is 32.06 plus 4 oxygens. 4 times 16, about 132.2 grams in a mole of ammonium sulfate. My mole bridge has it at 2 moles of ammonia for every 1 mole of ammonium sulfate. I get about 2.27 moles of ammonia. So now I know what the moles of ammonia is. I can just plug into my ideal gas law. The pressure due to the ammonia was 1.15 atmospheres. I'm trying to find volume. My moles is 2.27 moles of ammonia. Gas constant is 0.0821 liter atmospheres over mole Kelvin. The temperature was 15 degrees Celsius, 288 Kelvin. So my volume is going to come out in liters. 2.27 times 0.0821 times 288 divided by 1.15, about 46.7 liters. So in these problems, I think the toughest one are these collecting a gas over water problems. So just realize that the first thing you need to do is correct the pressure. And they're always going to give you a table of these water vapor pressures. So you correct the pressure by subtracting out the pressure due to water. Then you'll have the correct pressure to plug into your ideal gas law so you can get the number of moles of the gas. Then you use the mole bridge to get the answer you're interested in. Good luck.